Okay, so we're going to continue working with probability and tables. We're going to start looking at some tree diagrams and stuff like that. So we've looked at how to find the probability of A, how to find the probability of B, the probability of A and B, the probability of A or B. We've looked at complements. Now we're going to make it more complicated. We're going to look at conditional probability. And conditional probability means that there's a condition to it. We have a little bit of a condition, and so the probability that one event happens given that we know an event has already occurred. So let's see, what's the probability that I'm going to get an A on a final given I have gotten an A on every single test so far? So that changes my probability because now I have extra information that may increase my odds or decrease my odds. And so we're going to look at how we change that. Now, how do we write that notation? So it looks like P parentheses B and then a straight up and down line in A. And so the way we read this is that the probability of B given A has happened. And so we're going to look at our tables and figure out how we calculate that from our tables. So in our first problem, we have the probability of A given B has occurred. So the idea is if we know that B has occurred, then we can't even look at B complement because now there is no B complement. We know B has occurred. And so to calculate the probability of A, I'm going to take the probability of both over the total probability of B. And so now we get kind of a formula here. This is the probability of A and B over the probability of just B. So on the bottom is what we know has happened. That's our new total now. That new total is the probability that B has occurred because now I know that's happened. So on my next one, the probability of B given A, so now that I know that A has occurred, this pretty much goes away. So now I want the probability of A and B over just the probability of A. And so again, we're seeing this formula, probability of A and B over what I know has already occurred, the probability of A. Now this formula is actually on your formula sheet. But if you don't understand how that pulls together with these tables, it makes it really hard to work out. So on our next one, the probability of A complement given B. So if I know B has occurred, I'm going to get rid of B complement. And the probability of A complement given B. So the probability that they both occur over what I know has already occurred. And now that just looks like a weird 8. Or 2 donuts together. Okay, so the next one, the probability of B complement given A. So again, I'm given A has occurred, so I know AC cannot occur. So I want to know the probability B complement has occurred when I know that A has happened. So this would go on the top, and this would go on the bottom to help calculate my probability. And then our last one, the probability of B complement given A complement. So if I know A complement has occurred, A is no longer an option. We want to know the probability B complement has occurred over the total that A complement. And so again, top and bottom. And so being able to map that out makes it so much easier to work with. So now we're going to see this thrown into our mix along with all the other probabilities we've been working with, because they're not going to just go away. We still have to look at them. So we have a sample problem. We have the events, E, which is the grade that comes from an EPS course, and L, the grade is lower than a B. Okay, so the grade coming from EPS course is really talking about the engineering and physical sciences. So here is our E, and then L is a grade lower than a B. So here is our L. So our first thing is what's the probability of L? So I'd want to look at my total L's, grade lower than a B. So this would be, it looks like 3656 over 10,000. So that's going to give me a value of 0.3656. And we can always turn it into a percent, but this is totally valid as a probability, 36.56%. Okay, the probability of E given L. So I know L has occurred, so pretty much I'm not even paying attention to this. And so I want to know the probability of E. So my E for that group is 800 over my total for L, 3656. And that's our conditional probability. So 800 divided by 3656, 0.2188. Okay, for our next one, the probability of L given E. So I know E has occurred. So now I'm pretty much ignoring this, and I want to know the probability that L has occurred given E has occurred. So the probability of L was 800 over the total for E, which is 1600, which I believe is 0.5. Which is a pretty high probability for engineering physical sciences that the grade's below a B. Okay, and that's how our conditional probability works. So let's look at another problem. If we know that a person owns a home, what is the probability that the person is a high school graduate? So now we've got to think about, how is this conditional probability working? Well, we know the person owns a home. So when I'm looking at this, given owns home. We know they own a home. So now I want to know the probability that they're a high school graduate. So high school graduate. So I'm going to find this probability. So I know they own a home. So I'm pretty much only looking at the homeowner part. And I want to know what's the probability they're high school graduates. So I'm going to look at the high school graduates for that. 221 over my total for homeowners. So 221 divided by 340 gives me 0.65. Okay, now our next question, if we know the person is a high school graduate, so our given information is a high school graduate, what is the probability the person owns a home? So this is a backwards one. So now we know they're high school graduate. So I'm ignoring this. I'm only looking at this area here. What's the probability they're a homeowner? So 221 out of the total number of high school graduates. So a little bit higher of a probability. Okay, why did I show you both directions? So that way you could look at a question and you can tell which one goes a certain way and how do you figure that out and how you line that up. And then there's also another reason, is we have this idea of independence. And independence is very, very important in probability and statistics. For two events to be independent, one event has to have no effect on the other event. In other words, they're independent if the probability of A given B is the exact same thing as the probability of A, because B should have no effect on that. And those are things that we can calculate. We now have the ability to calculate this. So to think about how independence works, think about this kind of socially. So the big dance is November 1st. Katie has a crush on John. But John has a crush on Freya. But Freya has no idea who John is. So if John goes to the dance, will it affect Katie's choice to go? Probably. Since Katie has a crush on John, she's going to try and take this opportunity to go to the dance, hang out with him, try and catch his attention, and hopefully see where things go from there. So this is yes. John going to the dance will affect Katie's choice to go. That means this is not independent. Katie's choice is affected by John's choice. They are not independent. And we call that dependent. Her choice may actually be totally dependent, maybe not totally, but it is affected by John's choice. Okay, if John goes to the dance, will it affect Freya's choice? Now, John has a crush on Freya, but Freya doesn't even know who he is. So that's not going to affect how she chooses to spend her evening. So this is no. And this would be independent events. Helps if I can spell that correctly. Because the probability of her going is not affected by his choice. And so that's just kind of the idea that we want to keep in our head. So we're going to go ahead and practice checking for independence. So is there a relationship between gender and having allergies? To find out, we used a random sampler at the United States Census at School website to randomly select 40 U.S. high school students who completed the survey. The two-way table shows the gender of each student and whether the student has allergies. Are the events female and allergies independent? So now I have to look at this relationship. And I actually have two options. I can check the probability of female given allergies and see if that's the same as the probability of just being female. Or I can check the probability of allergies given female and see if it's the same thing as the probability of just allergies. Meaning that given really had no effect on it. And so we can go ahead and do this. So I'm going to go ahead and do the blue one first. So the probability of being female, 23 out of 40. Now the probability of being female given having allergies. So I know that allergies is the only option. And there are 10 females that have allergies out of the total number of allergies together. So we're going to check these values and see if they're independent. .5 repeated. And this is 0.575. And since they are not equal, they are not independent. Now if we were to do it the pink method, the probability of having allergies is 18 out of 40. The probability of having allergies given female, so now I know the only option is female. And allergies, so 10 people have allergies out of 23 females. And now I can check that. So 10 divided by 23 is 0.43478. 18 divided by 40 is 0.45. They're close, not the same. So these are not independent. So now we have the ability to check for independence rather than trying to think through that. Other ways that we have independence. So if we're taking a card from a deck of cards and we do not put it back, now all of a sudden my second probability is dependent on what card I kept out of there. So when we replace cards, we have independent situations. When I do not replace cards, we have what we call dependent situations, or not independent, because the card I took out of the deck on the first draw affects the probability of the second. Okay, so we have gender and dominant hand. And we want to check to see, are the events male and left-handed independent? So we're going to go ahead and we're going to check the probability of left-handed given male. So right now we're saying male is our only option. We have 3 that are left-handed out of the total 23 males. So 3 out of 23, 0.1304. And then the probability of left-handed, so we have 7 left-handed out of 50. .14. Close, but not close enough. Okay, so now we're going to look at drawing some tree diagrams and situations like that. So we're going to draw a tree diagram for flipping a coin twice. So tree diagrams are great when you have multiple events occurring. So the first time I flip a coin, I have 2 options. I can have heads or tails. Since these are equally likely, they have a probability of 0.5. Now, for my second flip, if I threw a heads first, I now have the probability of heads or tails. And each one of these have a probability of 1/2. If I threw a tails first, I have the possibility of getting heads or tails. And each one of these have a probability of 1/2. Now the way our tree diagram reads now is now we have these possibilities. Now I have a possibility of, this could have been heads the first time, heads the second time. Heads the first time, tails the second time. This one is tails the first time, heads the second time. And then tails the first time, tails the second time. Now because we know these are all equally likely, I really have a 1 out of 4 shot for each of them. And a 1 out of 4 shot is also known as 0.25. Now, how did we get these numbers 0.25? Other than just looking at that. How can we mathematically come up with that? Well, because these are independent events, and that's why we talked about independent first, I can actually calculate this probability by doing the probability of this one times the probability of that one. But only if it's independent. And so now we get this idea of how we can work on and break down different things. Now we can also turn this into a table if we wanted to. We could say this is my first throw, over here is my second throw, and on my first throw I could have heads or tails. On my second throw I could have heads or tails. Now the probability of getting heads on my second throw is 0.5. The probability of getting tails on my second throw is 0.5. Heads on my first throw is 0.5. Tails on my second throw is 0.5. And then here, the probability of heads and heads, if they are independent, I can times those two values together. So now I could do 0.5 times 0.5, which tells me my probability is 0.25, which allows me to break down the rest of my table. And this is going to be a great thing for you to have to fill in those tables, because now they don't have to tell you what A and B is. They can just tell you that they are independent, and you can calculate it by taking the probability of A and timesing it by the probability of B. So here is that general multiplication rule. If A and B are dependent, then the probability that events A and B occur are going to be the probability of A times the probability of B given A has occurred. Because A changes the probability of B, we have to change that idea. Now, this is a conditional probability, and we've talked about how to calculate a conditional probability. And so if A and B are independent, then we can just go ahead and multiply the two probabilities. Because remember, if they're independent, this value is exactly the same as this value using that independent rule. So we're going to go ahead and we're going to look at drawing a tree diagram. And I don't like tree diagrams a lot, but the stats test will use them. So you have to be familiar with working with them and creating tables and all that, because they're going to throw information to you in a lot of ways. If we can create a tree diagram and then turn it into a table, because that's, for me, that's how my brain works. So I can draw the tree diagram, turn it in the table, and work with it that way. Okay, so we're going to do a problem. Suppose 18 out of 40 students had allergies. So let's say first student had allergies, or the first student did not have allergies. So if 18 out of 40 students had allergies, then how many did not have allergies? Well, how many is left over? Now, I'm choosing two students. Now I have to think about, are they independent? If I choose one student, do I choose another student again? Can I choose Josh and then choose Josh again? No, that doesn't really make sense. So these are going to be dependent events. So now, after I choose the first person, the second person could have allergies or no allergies. But my probability has changed now, because here my first person has allergies. Now I only have 39 people to pick from. And I already picked one person who has allergies, which means now I only have 17 students who have allergies. But if my first person has allergies, I still have 39 to pick from the second time. And now, if 17 of the 39 have allergies, how many do not have allergies? Okay, so now here, so this is a not dependent or not independent problem, because who I picked the first time affects who I picked the second time, because it changes the probability of that second person. So now let's say the first person I picked does not have allergies. So now I have an option of allergies or not allergies. So if the first person does not have allergies, now I'm down to 39 people. Now how many of those 39 people have allergies? So now my allergy number did not go down any. I didn't take any out, so this is still 18. But my no allergies did go down one, so this is now 21. And so this is how that whole tree diagram works. There's a lot of thought going into how this works, and that's what makes stats so frustrating, is because you really have to think about these intricacies of how it works. Now we want to know, what's the probability that both students have allergies? Well, the probability that I have allergies, then allergies, so allergy and allergy, should be my probability of A, 18 over 40, times the probability of A given A has occurred. So that's 17 over 39. So I'm still using the multiplication, but remembering that this value has changed because my choices were not independent. And so this will allow me to calculate that probability. So remember, when we're multiplying fractions, we multiply the top numbers. We multiply bottom numbers. 15, 60, and then we divide. Okay, playing in the NCAA. So we know that about 55% of high school students participate in a school athletic team at some level. And about 5% of those athletes will go on to play a college team in the NCAA. And then I believe there's another percentage, like 3% of them go on to play professional sports. So what we're going to do is we're going to kind of look at, okay, we have high school sports, no high school sports. So in our high school sports, we have 55% that play high school sports, which means 45% do not. Now I want to figure out how many of them play NCAA sports. And so now I know that 5% of this 55% goes here. Okay, so what I want to know is, whoopsie, I didn't mean to do that, is what number is really here. So I'm going to go ahead and use this idea that the probability of A and B, which is this area right here in my box, is equal to the probability of A times the probability of B given A. Well, I know my probability of A right here is 0.55. And the probability of B given A is the 5%, the 5% of that 55%. So I can use that multiplication rule to figure out what percent of high school students play a sport in high school and go on to play a sport in the NCAA. So now I'm going to go ahead and times the 0.55 times 0.05, and I get 0.0275, which tells me that 2.75% of high school students go on to play a college sport? So what percent of high school students play a sport in high school and go on to play a sport in the NCAA? 2.75%. Which is crazy. Crazy low. Okay, so weather conditions. Hacienda Heights and La Puente are two neighboring suburbs in the LA area. According to the local newspaper, there's a 50% chance of rain tomorrow in Hacienda Heights and a 50% chance of rain tomorrow in La Puente. Does this mean that there is a 0.5 times 0.5 equals 0.25 probability that will rain in both cities? And the true answer is no. And the reason why it is not appropriate to multiply the two probabilities, since the events are not independent. Because they are so close to each other, the weather in one will affect the weather in the other town. And so we just can't mathematically do that because there is no independence. But if there was a 50% chance of rain in New York and a 50% chance of rain in Hacienda, then it would be appropriate to multiply these probabilities, since it's reasonable to believe that the weather in Hacienda is independent to the weather in New York. And again, Gulf streams and all that may come into effect there, and there may be some sort of a relationship, but they are far enough apart that we could say that what's happening in that exact day is not affecting what's happening the same exact day in that other spot. And so that's our idea of independence. So I've kind of hit a little bit in spots here and there, but we're going to keep practicing this in class. And I'll see you tomorrow.